Now let's define pH. pH is simply an alternative way to express the hydronium ion concentration. It's a way to avoid having to use a whole lot of scientific notation to express the concentration in molarity. Before I define pH, I want to point out something about hydronium, H3O plus. All H3O plus is a proton plus water. So water is the solvent. So what I'm trying to tell you here is that H3O plus and protons are synonymous. Okay, so hydronium is essentially synonymous with the proton. So when I say H3O plus or H plus, I'm talking about the same thing because they're interrelated through a water molecule, and water is the solvent. So water is everywhere. Subtracting away that water molecule from hydronium just gives us a proton. So hydronium or a proton, both of those mean exactly the same thing. So what does pH mean? When I put a little p in front of something in chemical notation, that little p means negative log. And I'm talking about log base 10 here. So pH is literally the negative log of the proton concentration. An exactly equivalent way of saying that is that it's equal to the negative log, again, base 10, of the hydronium ion concentration. So all pH is a log transformation of the hydronium concentration, negative log of H3O plus. So if you have the hydronium concentration, you can calculate the pH by taking the negative log of it. And again, it's log base 10, not natural log. pOH is another concept, might be a little bit less familiar, but that's simply the negative log of the hydroxide concentration. So it's very easy to transform hydronium or hydroxide concentrations into pH or pOH expressions. For example, let's say we have a hydronium concentration of 1 times 10 to the minus 1 molar. What would the pH be? All you have to do is take the negative log of that hydronium ion concentration. And in this case, it's going to give me a pH value of 1. If we have hydroxide of 1 times 10 to the minus 6, and I want to calculate the pOH, all I would do is take the negative log of that hydroxide concentration. So this would give me a pOH value of 6. So we can say certain things. Remember that cutoff I had where hydronium is equal to hydroxide concentration at 25 degrees Celsius. Those are 1 times 10 to the minus 7 molar when they are equal. At that point, I could take the pH of that hydronium concentration and it would give me a pH value of 7. So we call that pH 7 a neutral solution. Okay, so if the pH is equal to 7, the solution is neutral. And the reason it is neutral is because the hydronium and hydroxide concentrations are equal at 1 times 10 to the minus 7 molar. Okay, so take the negative log of that and you get a pH of 7. Now, if the pH is less than 7, the solution is acidic. Okay, you probably know that from before. But why is that? The solution is going to be acidic in that case because the hydronium concentration is greater than 1 times 10 to the minus 7 molar. Okay, if it's greater than 1 times 10 to the minus 7 molar, then you have more acid than base in your solution. So the solution is acidic. Finally, if the pH is greater than 7, your solution is basic. And that is because in that situation, your hydronium concentration is less than 1 times 10 to the minus 7 molar. Therefore, your hydroxide concentration would be greater than 1 times 10 to the minus 7 molar, and your solution would be basic. So that's where we get that kind of cutoff value at 25 degrees Celsius. A pH of 7 gives me a neutral solution because I have equal concentrations of hydronium and hydroxide. Now, you can look at common household substances and see their pH values. I'm just giving you a chart here that shows the pH values of common substances. You can take a look at this if you would like. So the pH scale isn't just from 0 to 14. You can have negative pH values. You can have pH values above 14. But the common scale that we use is 0 to 14 for most things. Muriatic acid, hydrochloric acid, has a pH of 0. This depends on its concentration. I'll actually talk more about that later. So this is very dependent on the actual concentration of the hydrochloric acid. More important for you guys are the ideas that stomach juice, okay, gastric juice is very low pH, 1.2. That's because gastric juice is HCl. You can see that lemon juice and vinegar have pH in the 2 to 3 range. Fruits are full of organic acids, and that drops their pH to acidic values typically. Soft drinks like Coca-Cola also have acidic pH. Phosphoric acid is an ingredient in cola, for example. So most of the things that we put into our mouth actually have acidic pH values, as you can see. Now, as we get to the circumneutral values, okay, so here around 7, I would call that circumneutral. Circum is Latin for around, so these are circumneutral pH values. Then you start to get things like saliva and blood. So physiological pH is 7.4, the pH of blood, and that's buffered by the carbonate system we'll talk about a little bit in the future. In your mouth, you have slightly more acidic pH values. Rainwater varies very widely. You can have acid rain that drops the pH value to significantly below 6.5. One thing's not on here is seawater. Seawater pH is around 8, and it's always dropping these days because of ocean acidification, because of excess carbon dioxide in the atmosphere. So you can kind of see, and then you have on either end, in the very acidic end or in the very basic end, you have corrosive substances. So things like oven cleaner, very corrosive, drain cleaner, these would have pH values around 14. Okay, so that's just kind of an aside. Let's do some more, let's think about this a little bit more numerically. So let's think about the ion product constant. We know that at 25 degrees Celsius, if I multiply hydronium concentration times hydroxide concentration, I get Kw. Okay, so remember Kw is 1 times 10 to the minus 14. Now, let's do a quick derivation. I want to take the log of both sides. If I take the log of both sides and I use the law of logs, I can pull apart the hydronium and the hydroxide from each other. So I add them together, and that's going to be equal to the log of 1 times 10 to the minus 14. Again, I'm just taking the log of both sides and using the law of logs. Now, the log of 1 times 10 to the minus 14 is minus 14. So if the log of hydronium plus the log of hydroxide is equal to minus 14, well, let's reverse the signs so that I have positive 14 on the right and negative log of hydronium. and negative log of hydroxide on the left. Now, this should look familiar, right? The negative log of hydronium is pH, and the negative log of hydroxide is pOH. So I just derived a very important expression that the pH plus the pOH are equal to 14. That means that if I have the pH, I can very quickly calculate the pOH and vice versa. So let's put this into action. You guys should get very good at interconverting between hydronium and hydroxide concentrations as well as pH. I want to make a little number line where we have, I'll put hydronium concentration on the axis first. So I have 1 molar, 1 times 10 to the minus 4th molar. This is not really to scale. I'm just kind of giving you an idea of how this varies. So I'm going in decreasing orders of magnitude of hydronium concentration here. 1 times 10 to the minus 14 molar. Okay, so this is, I chose this scale for a reason. If I want to calculate the pH values at each of those points, then all I have to do is take the negative log of the hydronium concentrations. Here, let me use a different color for that. So the negative log of 1 is 0. The negative log of 10 to the minus 4 is 4. The negative log of 10 to the minus 7 is 7. The negative log of 10 to the minus 10 is 10. And the negative log of 10 to the minus 14 is 14. So you can see that as the hydronium concentration decreases, the pH goes up. Okay, so that, I hope that makes sense to everybody, because that's a little bit counterintuitive sometimes. Basically, the higher the pH value, the less acidic you are, but the higher the hydronium concentration, the more acidic you are. And that's because pH is the negative log. So we can also do the same thing for hydroxide. Now, looking at the hydroxide concentration, when hydronium is high, hydroxide is going to be low because of the ion product constant. Now, remember, OH minus times H3O plus is always going to be 1 times 10 to the minus 14, the Kw. So when hydronium is 1 molar, hydroxide will be 1 times 10 to the minus 14 molar. When hydronium is 1 times 10 to the minus 4, hydroxide is 1 times 10 to the minus 10 molar. When hydronium is 1 times 10 to the minus 7, so is hydroxide. That's the point of neutrality. And when hydronium is 1 times 10 to the minus 10, then hydroxide is higher, 1 times 10 to the minus 4, again, because their product has to be equal to Kw. Their product has to be equal to 1 times 10 to the minus 14. And finally, when hydronium is 1 times 10 to the minus 14, that means hydroxide is 1 molar. Okay, so hydroxide and hydronium vary inversely. And I could also put the pOH values here. Remember that pH and pOH sum to 14. So when pH is 0, pOH is 14. When pH is 4, pOH is 10. When pH is 7, so is pOH. When pH is 10, pOH is 4. And when pH is 14, pOH is 0. So you should make sure that you can interconvert between pH, pOH, OH minus, and H3O plus. If you have any one of these 4, you can calculate the other 3. Let's do some examples. Calculate the pH and the pOH of a solution that has a hydronium concentration of 4.3 times 10 to the minus 8 molar. All right, so if we want to calculate the pH, all we have to do is take the negative log of that hydronium concentration, 4.3 times 10 to the minus 8. The negative log of the molar concentration. That's going to give us a pH of 7.37. Now, I also want the pOH, and I know that pOH and pH sum to 14, so I can take 14 and subtract the pH, and that's going to give me the pOH of 6.63. Now, the pH is above 7, so this is going to be a slightly basic solution because I have slightly more hydronium than I would have, slightly more hydroxide than I have hydronium in this solution. Okay, let's do another example. Calculate the hydronium and hydroxide ion concentrations of a solution that has a pH of 6.40. Okay, so we need to be able to go backwards and forwards with this. So if I have a pH of 6.40, I know that pH is equal to the negative log of the hydronium ion concentration. So I need to pull that hydronium out from under the log. So the hydronium ion concentration, if I take 10 and raise it to the power of both sides, I can figure out what the hydronium concentration is. I can pull it out from under the log. So hydronium is always going to be equal to 10 to the minus pH, essentially. In this case, that's going to be 10 to the minus 6.40. So the hydronium, you can plug that into your calculator, 10 to the minus 6.40. In scientific notation, that would be 4 times 10 to the minus 7 molar. We also want to figure out what the hydroxide concentration is. There's a few ways you can do this. Probably the simplest way is to just use the Kw. Remember that the ion product constant Kw is equal to the product of hydronium and hydroxide. So I can get the hydroxide by dividing Kw by hydronium. So at 25 degrees Celsius, which is what I assume I'm at here temperature-wise, this is going to be 1 times 10 to the minus 14 divided by 4 times 10 to the minus 7. That's going to give me a molar concentration of 2.5 times 10 to the negative 8 for the hydroxide. So if you have any one of those parameters, hydronium concentration, hydroxide concentration, pH, or pOH, you should be able to calculate the other three.